Okay, so let's talk about circular motion more today and the equations you can use to demonstrate circular motion. So if you think about something moving in a circle, just a little ball spinning in a circle, and think about its velocity direction. Its velocity is tangent to the circle. So at any given point, this ball is moving at a line tangent to the circle. So if it's right here, its velocity would be pointing in that direction. If the ball is down here, its velocity would be pointing in that direction. Now it's constantly being pulled inward. There's a force, centripetal force, which is pulling it to the center. Centripetal force is Latin for center seeking. So it's a force that pulls something to the center as it moves in a circle. So as an example, you can think of something, a string being pulled around in a circle. And my hand provides centripetal force along with the string, and it keeps it in place. So when I move around a circle, what keeps it moving in a circle? My hand keeping the string along with the washer keeps it moving. If I let go, though, we know what's going to happen. It moves because it's not going in a circle anymore. My hand is what kept it going in a circle. My hand supplied centripetal force, pulling it to the center. So if the string were to snap, or my hand lets go, then it can't go in a circle anymore. Now, which way did it go? Well, I know which way it's going to move. I can predict. So I knew it wasn't going to go, I was going to go that way. I was going to go up the ceiling. I knew it was going to go to the side. Because if you think about its motion, when did I let it go? Well, I let it go when its velocity was tangent right here. So when it's down here at the bottom, its velocity will be moving to the side that way. And so I knew when I let go of it, it was going to go in a certain direction. So I didn't throw in that direction, I just let it go. But because I let it go at this point, its velocity was going horizontally to the right, and I knew that's the way it was going to go. Does that make sense? If you're moving in a car, you're just turning your car on a bend. I'm just going to just draw it out here. So you're going down a road, and it's curving to the side. And that's your car. So we're looking at a top view of your car. And your car is driving this way. It's always tangent to the circle. So if you don't pull your steering wheel, you'll just go this way. You're going to go off the road because your car would be going tangent to the circle, which would then pull you off the road eventually. But if you turn your steering wheel, centripetal force is what pulls your car inward. And that's what keeps you going in the circle. So if your car is now up here, the car's velocity tangent to the circle would be like this. So that's velocity, that's velocity. Centripetal force would be pulling it inward like this. And that's what keeps the car on the road. So if you let the steering wheel go, the car would just go straight, which would be going off the road at that point. So in both of these cases, whether I'm talking about a string with the washer on it or a car going around the road, anything that goes in a circle has to follow this rule. That centripetal force pulls things to the middle, that's what keeps it going in a circle. Another example would be planets around the sun. So the sun pulls planets to itself. So you have Mercury out here. Orbiting around the sun. What keeps it in motion? Well, the sun is pulling it to itself. So gravity between the sun and Mercury is what keeps the planet going around the sun. Now the planet's velocity is always tangent to the circle. So Mercury's velocity would be in that direction at that point, but the sun keeps on pulling it to itself. So any movement along here, its velocity tangent to the circle keeps it moving in a circle around the sun. With the car on the road, friction is what's applied as centripetal force. So the friction between the tires and the road is what keeps the car in the road. And that's why if it becomes icy or if it rains, you have less friction. You can't take a turn as fast. You can lose control because with less centripetal force, you can't go as fast on the road. So an equation that puts it all together is the centripetal force equals mass times v squared divided by r. Mass would be the mass of the object in motion. In the case of the sun with Mercury, you would not use the sun's mass. You would use Mercury's mass because Mercury is what's in motion. And r is the radius of orbit. The experiment yesterday, what you should have seen is that as you increase the radius, what happened to the velocity? Did you see what happened with that? With an increase in radius, what happened to the velocity? Yes. Yeah, it got smaller, right? And then what about increasing the mass? Like if you increase the washers, what did you see? You see an increase in velocity? No, you didn't? When you add more washers to it, did you see an increase in velocity or decrease in velocity? Increase, right? You should have, yeah. Because what you should have seen is that if you add more washers to it, you had to spin it faster to keep it in motion. And so what does that represent? Well, the more washers represent more force. Centripetal force is what the washers are pulling inward. So the experiment yesterday, you had the washer and you had washers down here too. So the washer down here is what supplied centripetal force because the washer down here was pulling the string downward. And that's what made this pulling motion that kept this in motion. And so by increasing washers down here, you're increasing centripetal force. Also the moving object. So we talked about how we have centripetal force going to the center. Acceleration is also moving to the center. So centripetal acceleration would be the same exact vector as force. It accelerates in the same direction as force. That's always true for anything. Force and acceleration are always in the same direction. When you have a force, you have acceleration in the same direction as the force you apply it. So if force is being pulled downward to the middle, it accelerates to the middle. So what this represents is that you can have a force vector here, but this also means just acceleration, centripetal acceleration. So A sub C stands for centripetal acceleration. So with the moving object around in a circle, it accelerates to the middle. Yes. They're the same direction. So they're in the same direction, but they're not the same number. They're different magnitudes, but just the same direction. There's two equations that you can use for acceleration. I'll give you both of them. It just depends upon which numbers you're given, whether you're going to use this one, another one. But for one of them, you can use looks like this, where it equals v squared over r. Another one that's a little more complex looks like this, where it's 4 pi squared r over capital T. And that stands for the period, which is how long it takes to go around one time. So the time to complete one circular motion is called the period, and it's capital T. So if you're given time and radius, you'd use this equation. If you're given velocity and radius, you'd use a top equation. So now there's three equations that will be helpful to you on your note card. Let's go through an example in your book. Let's see, where is that? It's on page 155. So it says that a 13-gram rubber stopper is attached to a 0.93 meter string. The stopper is swung in a horizontal circle, making one revolution in 1.18 seconds. Find the tension exerted by the string on the stopper. So this is on page 155, except problem number 2. So the string is 0.93 meters. So that's the radius of motion. We know the mass of the stopper. It was given to us 13 grams. Now we always need to use kilograms for these problems, so we might as well just convert right away to kilograms. So how many kilograms are there in 13 grams? Remember this? How you go from kilograms or from grams to kilograms? Kilo means 1,000. So there are 1,000 grams in a kilogram. Good, so you just divide it by 1,000. So 13 grams to kilograms divided by 1,000. 0.013 kilograms. It's the mass of the stopper. So we know the radius, we know the mass. We also know the time it takes to go around one time. So that's capital T. 1.13 seconds, 1.18 seconds. So those are all the things that we know. And it says to find the tension exerted by the string of the stopper. So what is tension? Well, tension is the force that a string exerts. So tension is pulling inward, right? Tension is what keeps it moving. Oh, t squared. Oh, sorry about that. Why did I have that? Oh, I'm sorry. Yeah, it is squared in my notes too. I just forgot that. I'm glad you pointed that out. That's a good catch. Yeah, sorry. That should be t squared. Just forgot to add that in there. Okay, so the tension in the rope is pulling inward. That's the force pulling inward. That's also what centripetal force does. So centripetal force is equal to tension because it's the same force. Tension is what pulls the string inward, so is centripetal force. So tension equals centripetal force. So if you find centripetal force, we have found tension. But not to be confused with, so I use capital T here for tension, but this capital T would be period, the time it takes to run one time. So those are two different capital T's. Okay, so we know that tension is equal to centripetal force. What we also know is that force is equal to mass times acceleration. So that's true for anything, Newton's second law of motion. So we can apply Newton's second law of motion to any situation where we have force. So we're trying to find tension. So if we find centripetal force, we have found tension. What do we have so far? We have the radius, we have the mass, we have the period. Let's think about the problems that we have, or what we have to work with. We have centripetal force equals mass times velocity squared over r. So do we know the velocity? We have the radius, we have the mass, we have the velocity. So what we could do is find the velocity, because we do know the time to go run once, and we know the radius, right? So we could get the circumference. And based on the circumference, we could then find the velocity, which then we could solve. We could also do is this. So we also know that acceleration times mass gives you force. Now the problems that we have, though, also requires velocity for this one. And then for the other one, what is that? 2 pi squared r squared over t squared? Oh, 4 pi, thank you. Oh, okay, good. I always forget which one's square in that one. So for this one right here, we do know t and we know r. So what we could do is use this equation right here and then multiply it times mass, and that gives centripetal force. So that's two ways we could go about it. Either of those would work. Yeah. First acceleration up here. Sorry, which one? Oh, yeah, v squared. Yes, I keep forgetting which one's square, which one's not square. I'm glad you're catching those ones. Sorry about that. But yes, that one should be v squared. So we could go two ways with this. We'll just do this one and put acceleration up here and multiply it by mass. That would give you the force. So we know the mass of the object was 0.013 kilograms. We can multiply it by the acceleration right here. So we have 4 pi squared. The radius was 0.93, is that right? 0.93? Yeah. And that's not squared. And then over t squared. And time was 1.18 seconds. So this what we have right here is M times A, and that gives you the force. Let me know when you get that. Okay, so that would be the acceleration, but we found not acceleration, we multiply by kilograms. So that wouldn't be meters per second squared in this equation. Anybody have it? 0.34. What would the units be for this one? Good, Newton's force. So that's the force. Centripetal force, which is also the same as tension. So tension would also equal the same thing. So the tension in the string is also 0.34 newtons. So whenever you have a rope going around in a circle, tension supplies centripetal force. So tension equals centripetal force when you have a rope going around a circle. If you have a car going around a bend, then you have friction, that the friction between the tires and the road that supplies centripetal force. And if you have a planet orbiting the sun, then you have gravity that supplies centripetal force. So it's important to know what force is causing centripetal force. And whatever force that is, it equals centripetal force. You know, so if you look at number 12, for example, on page 156, you know, there's a runner that goes in a circle, and it's asking what is the agent that exerts the force on the runner? Well, that's like the car and the road example. You have friction that causes the runner to go in a circle. So friction is the agent that causes the runner to go in a circle around the track. So if you have a moving object on a road, then the friction between the object and the road is what makes it go in a circle. All right, so go ahead and work on some problems on that page 156 for today, 12 through 21, but skip number 19. So these are all very similar to what we did on the board. It's really the same kind of setup where we have those three equations and you solve for the unknown. Number 19, skip that one. Yeah, if you want to go outside, that's fine. Yeah, you can work outside today. Oh, it's 12 through 21, but skip number 19. Yes. Yeah, friction between the shoes and the road is what makes the runner go in a circle.